and welcome to the next section in the chapter on hyperparameter tuning, which is a brief chapter or a brief section on pipelines and AutoML. So here we will study very briefly pipelines as kind of a network of connected steps of learnable operations. So for example, there might be some feature extraction and some pre-processing operations before we let the data finally flow into our machine learning model. And this would be something that we would call a sequential pipeline. And pipelines are important so we can connect these steps together as and form a single object out of them, a single learning algorithm object. So we can embed that object into cross-validation for unbiased evaluation of its performance, so that we can also hyperparameter optimize that object in an efficient and joint manner. What I will also do here at the end is spend a few seconds on pipelines as directed cyclical graphs, which can be used to construct even more complicated systems and construct, ensembles, or maybe even a first approximation of a full AutoML system that does hyperparameter optimization and model selection simultaneously. Okay, let's start. So I guess maybe a little motivation here for AutoML as a generally useful component of practical machine learning nowadays. So very often data scientists really, when they are trying to solve a modeling problem in data science, rely on trial and error. So very often we have to try out different forms of machine learning models because it's a priori not clear which model class might be best for a certain task at hand, and becomes even less clear if we consider pre-processing or feature extraction or other data transformation methods. And this is pretty tedious. This is not really reproducible. This is not really efficient, and we should probably not do this in a console through human trial and error. What we should rather do is kind of subject all of this trying out of different steps to an automatic optimization procedure where we actually define what we are looking for and the constraints of that optimization procedure, and maybe introduce some prior knowledge into that thing. But we define the goals and constraints of the optimization task, and then let a proper, efficient algorithm handle the rest. And this is what we want to discuss here a little bit. Of course, we discussed this before in hyperparameter optimization and tuning, but what I want to do here is want to generalize this also to pre-processing and other stuff, to more complicated machine learning systems, and these systems we will now call pipelines. Graphs of learnable steps where data and intermediate results flow through such a network. And of course, the whole machine learning lifecycle is much richer than just the modeling itself. Actually, one could argue that the modeling itself is kind of probably the easiest of these steps. Nevertheless, this is what we will handle here through an AutoML solution. Of course, there are also all of these other steps like business understanding, data acquisition, and exploratory data analysis, deployment and monitoring. And like I said, it could actually be argued that all of these steps here are much harder to kind of get right because we can't really easily come up with workflows for them that always or that they can be automated. But what I want to focus on here is how to kind of how to optimize the way the hyperparameter optimization and algorithm selection, model selection of that step here. So what's a pipeline, or what's a sequential pipeline? So usually in machine learning, like I already said, there are several data transformation steps that happen before a model fit happens. So here in my example that I came up with, so this is a very simple thing. Maybe we have a machine learning algorithm that requires us to scale our features, and maybe that scaling does not happen automatically in that learning algorithm. So maybe this is a regularized machine. I don't know, some system with L1 or L2 regularization, and in such a case, it's usually a good idea to scale all of the features. maybe this learning algorithm can only handle numerical features, so we have to do some form of factor encoding. And maybe it's a very high dimensional task, and our learner is not that capable of handling this super high dimensional amount of all of the features. And we think it might be a good idea to kind of filter down the features either for an extra form of regularization or for a trick to speed up the learning algorithm, or maybe to conserve memory. So we think it might be a good idea to actually have all of these 3 steps here in succession before we go into the learning algorithm. What is important now is to actually consider or have the insight that all of these operations here, they actually also have a training and a predict step, as has the learning algorithm. So there's training data that comes in, and then we learn something from that operation, from this. Of course, we're also transforming the data, but we're also actually learning something from this. So for example, when we are scaling, so maybe we are doing the kind of the default form of statistical scaling by going to 0 mean and unit variance. So that would mean that for each feature, we are actually learning, for each numerical feature, we are learning 2 parameters. So we are learning the mean value, and we are learning the standard deviation. And we would do something like, I don't know, do this operation here on the data, on the first feature. So you would subtract the mean and divide by the standard deviation. And that would result in a feature that has that has zero mean and unit variance. And the same for factor encoding and for feature filtering. I guess we also have to kind of store which features we are keeping. And so all of these guys here, they have learnable parameters, and these learnable parameters, they will be applied when test data goes in the prediction step into that pipeline. So when we are working on test data in the prediction step, we're not going to estimate again this mean value here and this standard deviation value. We'll just apply them. Yeah? The same for factor encoding and for feature filtering. We already know which features we are filtering down to. So we have this set of features stored, and then we will not kind of compute any information measure to figure out which features we wanna filter down to. We'll just apply what we have learned in the training step. And that we have this separation between this training and test step, and that we construct such a learnable pipeline from this. This is really important, so we are able to programmatically embed our pipeline into cross-validation, so we avoid overfitting and we avoid biased evaluation. So what we should usually not do is take our data, and then, so the joint train and test data, and then apply the scaling and factor encoding and feature filtering to that global data set, and then only cross-validate the machine learning algorithm on that transformed data set. So it's a very well-known fact that this can lead also to overfitting. So especially, I guess, for feature filtering, this might be obvious, because usually for feature filtering, we are doing something like having a look at, so how much can I actually learn from that single univariate feature about my outcome Y. And this means I'm kind of peeking at X and Y values simultaneously. And if I do this on the complete data set, it seems pretty obvious and plausible that this can result in overfitting if I then do not embed that into cross-validation. Unfortunately, this can even be true if I'm using unsupervised techniques, which do not even consider the Y. So in general, to stay on the safe side, it's probably a good idea to construct these pipeline objects here with training and predict steps. And this kind of keeps this general principle of using data, using only a portion of the data to train on, to learn our model, and in this case, learn the parameters of all of the pipeline steps, and then evaluate the resulting model on fresh new test data that we have not seen before during the training. We can actually make this more complicated by moving from sequential pipelines to full graphs. And if we do that, we can handle a very, very nice extra problem with that. You can actually do a lot more, and don't really want to go into that here. So just want to motivate one thing, and this is some people call that actually cache. So that's the combined algorithm selection and hyperparameter optimization problem for machine learning. It's just a neat acronym. And hyperparameter optimization we have discussed before, right? So maybe I should also say that about sequential pipelines. So of course, all of these different different learning steps, they have some hyperparameters. So this learning algorithm for sure has some hyperparameters, but maybe this feature filtering or factor encoding procedure has hyperparameters as well. I'm not sure whether I want to call them. I don't know. I want to use an index here because I usually use that for components. I don't know. I'll put some, I don't know, multiple tildes on them. So, okay, that's probably a bad idea. It makes it very chaotic. But anyway, so I have these 4 components here. And of course, I can just join them together and then have the joined hyperparameter vector lambda, which contains all of them. And now I can use any of the tuning procedures that we covered before. It's probably a good idea now to really choose something that's quite efficient, because the one thing that has changed structurally, the hyperparameter optimization problem has not changed that much. The one thing that has changed is that it has become more high dimensional, right? Because I have now these multiple components and a much longer vector of hyperparameters. But the other nice thing I can also do is I can now try to figure out, again through hyperparameter optimization, which learning algorithm or which feature filtering or which factor encoding algorithm to use. And some people would call that, I don't know, discrete model selection, and other people would call that, I don't know, algorithm selection. And this cache means I would like to combine these discrete choices of which algorithm component to use, and also to figure out how to configure their hyperparameters. And one way to write that down, this is how we are doing this in R, and for example in our MLR3 package. But there are very similar ways of doing something like this in Python and scikit-learn and other toolboxes, as to, for example, write this. You can either write this as a kind of hierarchical structure where you have here a pipeline component, and in this pipeline component there are actually like inner components that you can select. And what we are rather doing is making that or representing this choice, which component to take, by configuring a graph and configuring how data flows in such a graph. So one way now to define such a pipeline is to say this is a directed acyclical graph of nodes and edges, and data flows through that graph. And each node in such a graph is some data transformation learning operation. Yeah? So we call that a pipeline operator. You can call that a data transformation step or a learning step or whatever. Yeah? So what you could, for example, put in such a node here is, for example, something like a PCA operation or a GLMNet operation. So that would fit a regularized linear model or a support vector machine or boosting. Yeah? And I don't know, scaling would be such an operation, or factor encoding would also be such an operation. And what we're now introducing here are so-called branching operators. So you have a node here, and that node doesn't really do a lot of, fancy data transformation. The only thing that it does is it decides whether data or intermediate result objects flow here or there. Yeah? So they can either go left or right, or maybe they also 3 or 4 paths. Yeah? Here are 3 paths. And this node, which we call a branching node, that node has a single hyperparameter which simply controls which of these paths here becomes active and where the data flows. So if you have that, what you now can do is you can come up, or you can kind of design a system which, for example, does factor encoding in the beginning, maybe always the same. And then in the second step, you can do a principal component analysis on the numerical data, or you don't do that. And in a third step, you can either use machine learning model A, B, or C, so GLMNet or the support vector machine or boosting in the last step. And these hyperparameters you now expose to the tuning algorithm, and you actually have your hyperparameter optimizer figure out which is the most efficient task to take. So maybe it would be, okay, I guess factor encoding we always have to go through, then it's PCA, and then it's boosting, and the hyperparameter optimizer figures out that under cross-validation, this configured path of the graph actually results in the best cross-validated performance. So what happens now in terms of hyperparameter search spaces? So again, we kind of combine everything together and we get that joint search space, which is usually of larger dimensionality. So again, it's important to use an efficient technique for hyperparameter optimization. Maybe Bayesian optimization, maybe something else. The one thing that structurally usually changes here is that let's assume that we had a simpler that these sequential pipelines usually can result in a already mixed numerical categorical search space. What usually happens here for these pipelines, it definitely becomes categorical because you have these categorical choices in there. Should I go left, right, or middle? But you also usually now have dependent hyperparameters. So if you're using the SVM, all of the hyperparameters of the SVM will become active. If you're using boosting, all of the hyperparameters of boosting will become active, and you have a complicated hierarchical search space, which is not a nice clean cross product as we would usually like to have to run our black box optimizer. So this makes HPO a bit more difficult, more involved. You usually have to construct special variants of your HPO algorithms so they can handle these search spaces. But in a certain sense, we can now define, this is one way to kind of construct AutoML systems now, combining such a flexible graph language to express machine learning pipelines with an efficient tuner. We could say this is AutoML, and that can hopefully handle these configurable pipelines and graphs, and are hopefully flexible enough to work on a quite large number of data sets from a large domain. Of course, there are a lot of challenges left. This was a very, very high-level summary here of the field. It's still pretty unclear what is the most efficient approach for AutoML. It also doesn't necessarily have to be reduced to hyperparameter optimization. So some people also like to reduce this more to constructing complicated large-scale ensembles. Would also be a nice idea if we can figure out a good way into this efficient optimization procedure, if we can figure out how to integrate human a priori knowledge or extra constraints or preferences in such an fully automatic procedure. It would also be nice if we can actually insert another form of more computationally obtained experience into AutoML. So on top of human a priori knowledge, we maybe would also like to include information about whether certain areas of the search space or certain components worked well on similar tasks in the past. So perform some form of transfer learning, maybe through warm starts, maybe by also learning search spaces or learning densities over search spaces, so we can more efficiently handle them and not always start from scratch if a new data set comes along and we want to configure our pipeline. Multi-objective optimization is usually interesting. It's usually interesting to also have secondary or tertiary goals in there of the machine learning pipeline that encode interpretability, or that encode sparseness, or that encode fairness, and so on. And another problem that usually exists nowadays for AutoML, that people already kind of have issues with trusting machine learning in general and would like it to be explainable, interpretable. The same, I guess, holds true for AutoML as well, right? So if there's some black box machinery now running and constructing a complicated system for them, people are somewhat reluctant sometimes to use that because they have no idea how the configured and constructed system in the end came about. And it's probably a good idea if we explain that back to users, how that process worked.